This is the second video about molecular shapes. We're going to cover Sp2 and Sp hybridization. So Sp2 hybridization is where you're going to have 3 bonding areas. So, if you think of there being a 1, the total of 3 bonding areas is what you're going to see. And boron is a good illustration of this. Boron, how we draw it like this, you can see then that it would want to bond 3 times, and it will want to end up with 6 valence electrons. So that's an exception to the octet rule, and it's one that I do want you to know. But why do we draw it this way? The electron configuration is 1s2, 2s2, 2p1, so it looks like there's only one time it can bond. But in reality, one of these s electrons will become promoted up into the p, and then these 2 orbitals will essentially morph together into a new set of equal energy orbitals that are in between the s and the original p. So that's what we call Sp2 hybridization. We're going to go to your note sheet, and the Sp2 hybridization, the geometry name is called Trigonal Planar or Trig Planar, but that's because the total number of bonding areas is 3. But there's 3 different shapes within this. So let me show you. So the first kind of shape would be if you have a central atom and you have 3 things being bonded to the central atom. And notice there's no lone pair of electrons. So let me show you with the FET. So this would be like 1, 2, 3. So notice the shape is flat, like a pancake kind of. So if I line it up right, you can't even see. So that's why the name of this shape is planar. It's called trigonal or trigonal planar. So an example of this is usually going to be boron, and this is, like I said, an exception to the octet. If you were to do a Lewis structure and use your electron cache and everything, you would kind of be out of electrons after you place them around like these chlorines. And then it's really tempting to want to double bond and give boron 8, but it doesn't need 8. It's an exception to the octet rule. It's fine with 6. Another thing is the halogens and hydrogen, so group 17 and hydrogen, they don't double bond ever. They only bond 1 time. So you're left with just these 6 valence electrons, and that's okay for boron. So if we look at so we have 3 bonds, and we have no lone pairs, and the ABE notation would be A, remember it's the central atom, B, there's 3, and then there are no lone pairs. So let me show you another one. The next type, again, we'll look at this. So it's possible to have, at this point it's linear, but have just 1 pair or lone pair of electrons. And this is bent. We did have a bent in the tetrahedral geometry. That bent had 2 lone pairs. This one only has 1 lone pair. So Sp2 hybridization means there's 1, 2, 3 total bonding areas. 2 are bonds, 1 is just a lone pair of electrons on the central atom. So we'll go to our note sheet, and we would have a central atom A with 2 bonds and then 1 lone pair. So an example of this could be, I'm going to give you one that's a polyatomic ion. and it's going to be double bonded to oxygen and single bonded to a fluorine. It's not one of the polys that we know, but it's a good illustration of this. So it's overall a -1 charge. And if you look at, there's also a lone pair on the top. It has one bond here. This is a double, but we're still only going to call it another bonding area. So we have 2 bonding areas and 1 lone pair for a total of 3, which it should be because we're talking about Sp2 hybridization. So we have 2 bonds and 1 lone pair. Again, these are adding up to 3. So it would be AB2, E1. And I can show you that on the PHET as well. So that would be, I'll clear it. So we would have, one of them would be a double, one would be a single, and then 1 lone pair. So that's an example of the bent shape, and it's due to Sp2 hybridization. Lastly, we have linear, and linear is when you're only going to have those 2 atoms. One of them we'll call the central atom, the other not, and you'd have 2 lone pair electrons around the central atom. So on the PHET, it would look like this, but then 2 lone pairs. And again, it's going to be just linear in a line. And let me give you a real example. So diatomic oxygen is an example. So we have, again, remember it's a double, but we call that 1 bond, 1 bonding area. And then what you need to do is just pick one of the 2 oxygens to be your central atom. It doesn't matter. So if I'm looking just at this oxygen, for example, it has that 1 bonding area here and 2 lone pairs. So the ABE notation would be AB1, E2. One more type of hybridization. This is called Sp hybridization. It's another result. It's another element that will have an exception to the octet. Beryllium is the one that's most common here. So beryllium is, 1s2, 2s2. So if we were to draw beryllium, that's why I make you go to 12 o'clock and then 3 o'clock, so you can see that it would then have 2 areas where it could bond. So what happens is one of the 2s electrons goes out into a p orbital, and then these morph together and become what we call an sp equal energy orbitals that are in between energy of the s, the 2s, and the 2p. So let me go back to this. I need to move my picture. Okay, so this would be, it could look like this. So 2 bonds, no lone pairs. It could also be 2 double bonds, again, 2 bonding areas, no lone pairs. It could be A with a single and even a triple. Again, 2 bonding areas, no lone pairs. So we're going to say 2 bonds, 0 lone pairs. So it's going to be AB2. And example could be this one over here would be if I had beryllium, and maybe it's bonded to a hydrogen and a chlorine. So it only ends up with 4 valence electrons, and that is an exception to the octet, and you do want to know that one. So that would be like this one over here. Let's look at this one here. This could be like carbon, triple bonded to a nitrogen, single bonded to a hydrogen, and you can see carbon has 2 bonding areas, no lone pairs. So that's all I have.